Okay, so we have started discussing about the turboprop engine, then now we are going to move to the turboshaft engine, and then we will continue with the some of the other parts, but let us look at the turboshaft because what we have finished, like the comparison with the turboprop with the turbofan, and now we are going to look at the turboshaft. So, this is also going to be a small section. This also kind of engine is a form of gas turbine, which is optimized to produce shaft power rather than jet thrust. So, this produces shaft power, not the jet thrust. Generally, a turboshaft engine is made up of two major components. One is the gas generator, another component is the power section. So, the gas generator consists of one or more compressor, combustor chamber or turbine, and the power section actually consists of an additional turbine or a gear reduction system and the shaft output. So, and there are different example of turboshaft manufacturer, like one is the biggest is Pratt and Whitney, they have PT6 and PT6A, these are the engines. Then GE also manufactures some of this, like it has S61, S62, then also so that power this aircraft. So, the engine is T700 or CT7, these are the engine. Then also Allison Engine Company, Lycoming, Rolls Royce, all these, and so the Soviet also, they also manufacture this kind of turboshaft engine. Just to look at the analysis of a turboshaft engine, let us say if we look at a single pool engine, then the engine will, the schematic will look like this. We have a then there is a turbine sitting there, then you have the load. So, this is a single spool turboshaft schematic. So, one can think A, 2, there is the combustion chamber, then 3, this is 4, 5. So, you can see this, the load is driven by the same gas generator shaft or driven by the free turbine. So, this is a single spool configuration, and the similar one we can. So, the TS diagram, if we plot of the same engine, it will look like starting from here, it will go there, and then from there it will come here. So, this is 3, here the PA is P02 equals to P5, this is 5, this is 4. So, that is the, and if we look at, so it has we can single pool engine. So, this is analysis would be quite similar to turboprop. Now, what we can do, the single pool engine, spool engine, we can look at the turbine. The turbine does both the compressor and the load. So, assuming full expansion in the turbine, so the shaft power would be 1 plus F minus B eta mt W T minus W c by eta m c, where F is the fuel air ratio, B is the bleed ratio, and the mechanical efficiency is eta mt, compressor efficiency is eta mc. Now, the shaft which drives the load, it could be the load which means, let us say for example, the rotor of the helicopter experiences some of the mechanical losses due to friction. So, the W load would be eta m W shaft. So, then we can find out the P load would be m dot A W load. So, that is how we can get it. Now, similarly, like a single spool, we can have an 2 spool turbo shaft also, and there is a different station number, and if you draw the TS diagram similarly here, this is from where it goes like that. So, this is 3, this is 4, and this is 5, this is 6, PA, P02, P6. So, now the twin spool also. Now, if you look at the gas generator turbine, so if you have the gas generator turbine, so that turbine provides sufficient energy to drive the compressor, and thus the outlet temperature is obtained from the energy balance. And how do we get it? Is a simple similar analysis that we have done. It is Wc by eta mc. So, that gives a T05 is T04 minus Cpc, T03 minus T02, Cpt, eta mc, eta mt 1 plus F minus B. And similarly, we get P05 is P04 1 minus T04 minus T04 by eta T T04. So, now free power turbine. The free power turbine, if you look at, the gases are basically have a complete expansion and to the ambient pressure. So, the power delivered to the load would be P load is m dot A 1 plus F minus B eta m Cp Ft T05 1 minus Pa by P05 gamma T minus 1 by gamma T. So, that is how the analysis actually holds for turbo shaft engine. Now, so that is how you can have single spool or double spool turbo shaft. I mean, the detail other component detail analysis we can carry out in the similar fashion that we have done for turboprop or any other turbine engines. Now, with that we will move to the one which is propeller fan. Okay. So, this is a modern type of aircraft engine related to concept of both the turboprop and turbofan. So, that somehow uses both the concept of turboprop plus turbofan. So, that is sort of a combination, but distinct from both. The engine uses a gas turbine to drive a unshielded propeller like a turboprop, but the propeller itself is designed with a large number of short highly twisted blades similar to the turbofan engine. For this reason, the propeller fan has been variously described as, this could be called as unducted fan UDF, or call open rotors which is OR, or it could be called ultra high bypass, that is UHB turbo fan. So, this could be also said like that. Now, it has a small diameter, highly loaded, multiple bladed variable pitch propeller, a propulsor having swept wide chord blades. So, propeller fan is designed to operate with a turbine engine and using a single stage reduction gear. So, it has an reduction gear that results in high performance. So, the performance is high. So, the design is sort of intended to offer the performance of a turbofan with the fuel economy of turboprop. So, most common arrangement for propeller fan is a 2 spool gas generator, 2 spool gas generator and aft located gearbox driving a pusher fan. So, with aft located gearbox driving a pusher fan. So, this fan produces the majority of the thrust. It has number of blade which is greater than the propeller of turboprops, but less than those of fan in the turbofan. Similarly, so one can see like there are also some historical thing, there is a history behind this kind of things. So, like some old, like here is an example of open rotor. So, this is like this is a G introduced this unducted G36. This is an aft mounted open rotor fan system with 2 rows of counter rotating composite fan blades. So, this was in 1980s. It is of the pusher configuration. The core was based on GF04 military turbofan. So, exhaust gases were discharged through a 7-stage LP turbine. Each stage ring was designed to move freely. So, the turbine rotor drive on propeller, while the other propeller is connected to the unearthed turbine stator and all this. So, the total in effect that power turbine has 14 stages, which you can see here. Now, the other one which one can see is also the one which is shown here, which is unducted fan in MD80. Okay. So, this is another one which is example of that nature. So, Pratt and Whitney engine one can see. Also there are other engine manufacturer which also they produce some engines of this kind of propeller fan, and they are in to some extent, like this is another one which is Pratt and Whitney 578 DX, which is 1980. This also having a reduction gearbox between LP turbine and the propeller blades. So, now some progress been made. So, this is our D27 propeller fan. So, this was developed by USSR. So, this is even conventional layout with propeller fan blades in front. So, it is used for propelling AN-70 aircraft. So, this was used for AN-70 aircraft. So, typically if you look at the classification of the propeller fan, there are 2 different types. One is the tractor type. So, if I look the prop fan, then there could be tractor type or it could be pusher type. So, these are the 2 different category which can be possible, and the tractor type propeller fan is similar to. So, this is one of the kind, like it could be saying the tractor type. or you can say puller type. So, this is an similar to forward fan with the fan placed. So, this is again the tractor fan can have two different kind. One is the single and another is the contra rotating or counter rotating, whatever it is. So, the example of contra rotating is this one. You can see this is the contra rotating. So, that is what is shown there. This forward rotor has 8 bladed while the rear is 6 bladed, and the pusher type, if one has to see, this is a pusher type typical arrangement of the turbofan, where it is similar to the aft fan, where the fan is coupled to the turbine. It is always of the contra rotating type. So, the two fan rows are driven by free turbine. This type would be more elegant as the engine would be placed behind the rear pressure bulkhead in the fuselage, minimizing the noise. It also allows an aerodynamically clean wing. Now, one can compare this like between turboprop, turbofan and propeller fan. So, if you compare that, propeller fan engines have the best known propulsion efficiency. Single rotation propeller engines have propulsion efficiency around 80%, while contra rotating can go up to 90%. So, main feature of propeller fan engine versus both turboprop and turbofan engines are quite significant. So, also we can see that, like for example, we can go here and see this comparison between all these turboprop, turbofan and this, and you have this, but you can see the propeller fan number of blades compared to turbofan less, but more than this, diameter is smaller, power is larger, blade type swift, maximum thickness thinner, tip speed supersonic, bypass ratio is 25, propulsion efficiency higher, ESFC is there, Mach number is around 0.7687, cruising altitude is 11,000. But open rotor pose some technological challenges, which like the open rotor kind of configuration, like noise and vibration, like then structural reinforcement of fuselage and wings. So, airworthiness consideration, engine installation and mounting, gearbox cooling and reliability, then design of efficient counter rotating components. So, these are some of the challenges with then competing technologies, because obviously that is another competing technologies. So, the current technology engine is improving on an average 1% per year, which means the traditional turbofan engine available in 2020 are likely to be at least 11% more efficient than 2010 production. So, that is an major technological breakthrough. Then we can, another is the slower aircraft operating speeds. So these are the some of these challenges which are there, and you can see this. So the other thing what is also possible, that there is a possibility of, this is a 3 spool configuration. So that is also possible. This is an unducted 3 spool configuration, and you have all this kind of, I mean, this is just an example that this is also possible, and you can have a TS diagram for this, and you can similarly look at the analysis. So for example, A to 2, 2 to 11 goes 3, this is 11, this is A, 02, 04, so this is 05, 06, 7, 8, so 9. So this one is 08S, and this is delta H, and this is alpha delta H. Now this one would be 9S, and here one can have, so this goes like there. So this is 010, and that also connect to PA, and this is 12. Okay, so these are the different portion. Now one can do this analysis, which could be quite sort of straightforward. So one has to look at first the intake, which is, this is probably the last one that we would like to discuss on turbofan, and that would pretty much finishes the. So if you have the, let's say, the flight speed, which is given u, and then ambient condition PA, TA, then you can find out gamma RTA. Then at the intake you can find out the Mach number u by A. So you get the T02, which is the relationship using that m square and P02. So we have done this so many times, but probably so diffuser or intake efficiency minus 1 by 2 m square gamma c by gamma c minus 1. Now intermediate compressor. So intermediate compressor, which is 2 to 3. So here P03 is P02 into pi IPC. So and T03 equals to T02 1 plus pi IPC to the power gamma c minus 1 divided by eta IPC. Now high HPC or high pressure compressor, which is 3 to 4. So P04 would be P03 into pi HPC. Similarly T04 would be T03 1 plus pi HPC gamma c minus 1 by gamma c eta HPC. Combustion chamber, which is 4 to 5, where P05 is P04 into 1 minus delta PGC, and it is 1 minus B into CPCC T05 minus CPC T04 divided by eta B QR minus CPCC T05. Then HPT, that is 5 to 6. So, energy balance for high pressure spool, from where we get CPC T04 minus T03, 1 plus F minus B CPH T05 minus T06. So, here we are assuming the transmission efficiency or the mechanical efficiency of the shaft and all this to be 100%. So, from here we get T06 minus if 1 plus F minus B CPH T04 minus T06, and P06 by P05, which is 1 by eta HPT 1 minus T06 by T05, which will be gamma H by gamma H minus 1. Then intermediate pressure turbine or IPT, which is 6 to 7. Again energy balance would give us T06 minus CPC by 1 plus CPH T03 minus T02. So, we get the pressure by P06 1 minus 1 by IPT T07 by T06 gamma H by gamma H minus 1. So, we get from here we get P07, from here we get P06. Then UDF or unducted fan. So, here T010 is T02. So, P010 would be PA 1 plus gamma C minus 1 by 2 m square minus 1. So, P01 is P01 into pi UDF. So, T01 T010 1 plus pi UDF gamma C minus 1 divided by eta UDF. So, what we get T12 by T011 PA by P011 gamma C minus 1 by gamma C. So, from here we get T12. So, unducted fan, it would be root over of 2 CPC T011 minus T12. So, that is what we get, and once you get that, then we have free turbine, which is 7 to 8, and hot nozzle, which is 8 to 9. So, from here we will write T9s equals to P07 by PA gamma H minus gamma H, which gets at 9s, and then temperature drop in free turbine would be T07 minus T08 eta FT T07 minus T08s equals to eta FT into alpha into T07 minus T9s. So, we get T08, we get T08s. So, from here we get the pressure ratio, which is T07 by T08s gamma H by gamma H minus 1. So, that gives us P08, and then the nozzle exit velocity would be 2 CPH eta n into T08 minus T9s. Now, so the thrust would give us m dot 1 plus F un minus u. So, that you get. Then finally, energy balance would give us beta CPC T011 minus T010 equals to eta m unducted fan 1 plus F CPH T07 minus T08. So, from here we will get beta, and then the thrust for which is obtained for TUDF is beta m dot UE UDF minus U. So, the total thrust would be total UDF plus Tn. So, and the power would be unducted power would be U into TUDF. So, that is how you can get, and then finally, you can find out the propulsive efficiency, which is T into U, and the total equivalent power is PT total into U. So, this is T into U into 0.5 m dot into U m minus U square plus beta U unducted fan minus U square. So, then you can get the propulsive efficiency. So, that is how you also can analyze the 3-spool engine, and that is pretty much kind of talks about this turboprop, turboshaft and turbofan engines. And the analysis you have seen already, this turbine based cycles, how the analysis is carried out. So, now you would be able to carry out the similar kind of analysis. So, we will stop the discussion here and continue in the next session in the other topics.